Then uh, the basic ideas we have discussed in the previous lectures about the design flows, the architecture, the basics of the VHDL code. In that VHDL code, we have studied library, then entity and architecture, or these three parts how we are defining in the VHDL code. Then in the next points, we will study the concurrent code, or in that concurrent code, the execution of that code takes place at a same time in the parallel way. Then in this or today, we will discuss the next points, and in that next points, the first point is nothing but the sequential code. So in that sequential code, the sequential codes are nothing but the codes which are executed one after another, or here one by one execution of that code takes place. And in that sequential code execution, so here we require one timings. So if one by one, or here every code is time dependent. So for that purpose, we are requiring the clock to that circuits, or in that sequential circuits. So the codes in these codes, the sequential codes are nothing but the processes, or in that process one by one execution takes place. Functions and procedures are only the sections of the code that are executed sequentially. Or one of the important aspect of the sequential code is that it is not limited to the sequential logic, or with it we can build sequential circuits as well as the combinational circuits, or in that combinational circuits we are also able to build. Or mainly the sequential circuits are nothing but the circuits which requires a clock, or we know that flip-flops as well as deep flip-flop, shift registers. These are nothing but the types of these sequential circuits, and the combinational circuits are nothing but the AND gate, OR gate, NAND gate. These are the combinational circuits. The sequential code is also called as a behavioral code, or here one by one execution takes place. So in that or in the concurrent statements from the previous section are useful in modeling combinational logic. Combinational logic constantly reacts to the input changes. In contrast, synchronous sequential logic responds to changes dependent on the clock. Many input conditions we are able to apply to that circuit, uh, and these changes, or the changes we are given in the form of the clock, and if that clock is changed at that time, the output state of that sequential circuit gets changed. So in that modeling sequential logic, we requires to model the activity of conditional on clock, edge triggered devices, sequence of operations, and so on. In this unit, we will learn VHDL process which help to model the sequential logic. And in that sequential logic, the these are the types. So in that first one is nothing but the process, or how we are able to define the process. Our process is a sequential selection of VHDL code. It is characterized by the presence of if statement, wait statement, case statement, or the loop statement, and by a sensitivity list. A process must be installed in the main code, and it is executed every time in a signal in the sensitivity list changes, or the conditions related to the wait functions. So how we are able to define that process, or a VHDL process has about following basic form, or it is firstly we are calling this one as a process. Then in that bracket one we are defining the sensitivity list. Then after that the next step is nothing but the begin, or in that begin we starts our execution, or here after that begin we starts to write down the sequential statements, or we are calling this one as a sequential codes. And after this all the codes are written, at the time we write as the end process, or here the end process and its label and a semicolon. So here when a process is used, the statements between the begin and the end, the statement between the begin and the end are executed sequentially. These statements are executed sequentially. The expression in the in this parenthesis after the word process is called as the sensitivity list, and the process executes whenever any signal in the sensitivity list changes. For example, if process begins with the process A, or we are giving the names to that process A, B, or comma C. And when the process finishes is it's executing, it goes back to the beginning and waits. After that ending of that, it goes back to the beginning and it ends or waits for a signal on the sensitivity list to change again. So the example which we are studying is nothing but the D-type flip-flop. Or here D-type flip-flop, it is also having only a single input, and we are using the input as a clock, because these are nothing but the sequential circuit, or flip-flop is a sequential circuit. So we require a clock, and this clock, or here the output of that D flip-flop is dependent on its input condition, or here that input value, the output is dependent, and that can be, or execution of that output can be takes place when we apply the reset button, or here that reset is for the who comes to the beginning state. But here the output value are based, or that q value is based on that input, but that values can be changed when we apply the clock, or we know that clock is up down, or 0 1 0 1 values we are input to that D flip-flop. So in that HDL modeling, we know that the modeling can be done by using the basic three steps. First one is the library declaration, the next one entity declaration, the next one is the architecture declaration. So firstly, the library. The library is nothing but the stored statements or from which we are using. So here that library we are using is nothing but the IEEE library, and that IEEE library we are using the logic codes, that is the IEEE.std underscore logic, that is the 1164, that all logic codes we are using. So that is the declaration of the library, there are two lines. The next one is nothing but the declaration of the entity, and in that entity how we are defining. So here entity DFF, that DFF means D flip-flop. The entity D flip-flop is, or here in that entity generally we are, or we are describing the input outputs presents to that architecture, or here the input are nothing but the D, then clock and reset, that three are the input values. These are nothing but the input std logic, and then q is nothing but the output value, and output we are separating, that is the q is nothing but the output std underscore logic, and in D flip-flop, or here the architecture, or here the inputs and outputs we are defining in that entity. The next part is nothing but the architecture, or in that architecture how this part is executing, or process of executing or execution we are defining in the architecture. So here the architecture behavior of, so first one is nothing but the architecture, or the architecture we are given the names to that architecture as a behavior. Behavior is named to that architecture. Then here capital of D flip-flop, DFF. DFF is nothing but the entity name. Here we are defining the entity name as a DFF is. Then next one, we are using the sequential statements to execute that D flip-flop output. So here in that sequential statement, we are using the begin, or in that begin, the process. The process can be defined by the changing value, that is the clock and the reset. So why we require that clock and reset? So whenever the clock changes, the process executes once through and then waits at the start of the process until the clock changes again. So here when that clock changes, the output can be changed and wait until that clock is changed. So the if statement, or here we are using the if statement or begin if statement, rst is equal to 1, then q is assigned to a value of 0. So here when that rst button is clicked, or here the rst is in the on, at that time the q firstly value of q is 0, then here the value of q is 0, else the value of that output is nothing but the clock here dash. The dash is nothing but we are calling this one as a tick, that is a clock tick event. Or here if the statement tests for rising edge of the clock, the q is set equal to the d. So here if that clock is in the form of the rising edge, or clock is as the high level, that q value is assigned as a d. When rising edge occurs, the clock expression clock dash, or here clock dash tick, clock dash event is used to accomplish the functionality of the edge trigger device. The expression uh, dash is a predefined attribute for any signal. There are the two types of the signal attributes in the VHDL. Those that return values and those that return signals. So here two attributes, or here there are the two attributes. First one is the attribute is that returns to some value and that returns to some signal. The dash event attribute returns a value, or here that uh, clock dash events that returns to some value, not as a signal. The expression clock dash, or here clock tick event, or here clock tick event is true whenever the signal clock changes, or that clock is true whenever that signal clock changes. If clock is equal to 1, or if that clock is equal to 1, it also true. This means that the change was from 0 to 1. Or here when that clock value is assigned to 1, at the time the change from 0 to 1, which is a rising edge. If VHDL is only for the simulation purposes, one might use statements such as if clock is equal to 1. So here, uh, based on that clock values, the DQ value is assigned. So if that in that Q, if reset is equal to 1, the Q value is assigned to 0. Else if that reset is 0 or there is no reset button pushed, at that time the queue assigns the value of clock tick event, and when clock is equal to 1, or here the changing from 0 to 1 takes place, at that time the queue assigns value of d. And end if, that is the end process, or that process stops until the next clock can be changed. So the statements between begin and the end, or in between that begin and the end process, end in a process operates as a sequential statements. In the preceding process, Q is assigned to value of D is a sequential statement that only executes the rising edge of the clock. In contrast, the concurrent statement, this Q assigns the value of D executes whenever D changes. But in that, whenever the clock changes, the value is assigned. So the next example we'll study, or here the D flip-flop alternative example, or in that alternative example, we are using a different way. So here we are inserting a wait statement, or here wait. So firstly, library IEEE, same as the before, use IEEE.std underscore logic underscore 1164. That is the same as the previous one. So entity or declaration of the entity is also same. Entity D flip-flop is, that is a port, that is the input ports we are defining D, clock, reset, that is the in std logic. These are all are the same, but only that architecture or in that process we are changing the statements, or between that process to the end process. So in that process to the end process we are using the wait statement. So here this process will execute the sequential statements until a wait statement is encountered. So that process repeats itself until that wait is encountered. Then it will wait until a specified wait condition is satisfied. If it will then execute the next set of the sequential statements until another wait is encountered. So it will continue in this manner until the end of the process is reached. Then we will start over again the beginning of the process. So here until that wait statement is executed totally or it reaches to that level, that the continuously execution takes place. After that wait statement is fulfilled, at the time it stops. But the stopping is up to the next wait statement is arise. So here we are able to give the time in that wait statement, or how much time you have to wait, or generally the wait time encountered is nothing but the 5 nanosecond. For a 5 nanosecond we will apply a wait time. So the next sequential statement is nothing but the case statement. So in that case is another statement intended exclusively for the sequential code. Case identifier IS, or here the case defining we are given as a case identifier. Identifier is nothing but the name of this case. So here when the value is assigned, or here assigned of that value comes as a given value, then that case statements is executed up till that the value is uh, given to its assigned function, or here the a is equal to 10, that is nothing but the key. Up till that will not come, that is continuously value is stored in that a. So case example, or in that example, the case control, or we have given the name that case is as a control is when 00 is assigned to value of x. At that time, the a is equal to, or here in that the output is 00. When that output is 00, when the x is assigned a value of a and y is assigned a value of b, at that time the output is 00. Then in the similar way, the output is 01 when the x is assigned a value of b and y is assigned a value of the c. Assigned means we are giving the values to that functions. If the two are not present, or here the two statements are not satisfied, then at that time we are assigning the value as a others, or here in that others the value of x gets value of 0 0 0 0. Others when x is value of 0 0 0 and y is value of z z z, and end case, or when we write start case, at that time when we have to write end case, and that end of that coding is takes place by the semicolon, or every statement we are ending by the semicolon. There is a presence of the semicolon. Only that starting one is not having a semicolon, but all other that is having the semicolon. Its semicolon indicates that the statement has been written and it is ended. So by using that case statements, or in the previous one we are using the wait statement, or here the procedure or simple statement. So by how we are explaining that example by using the case statement, here the library declaration is same, entity declaration is also same, then architecture, or in that architecture the declaration is different, or here DFF3 of the DFF, or here architecture name of that architecture is DFF3, and the name of that entity name is DFF, or here is the DFF is written. Then begin, then process, the process is mainly based on the clock and reset signals. So in that begin case statements, if RST or reset value is, or reset value is, or when that Q is assigned a 0, Q, or here we know that that is nothing but the Q. Q value is 0 when the reset is equal to 1. When that reset value is equal to 1, at that time the Q is 0. That is in the first statement. The next one, if that reset value is not 1, that what happens? When 0, the value of that clock, or here that Q is assigned to D, but that value is dependent on the if clock event and clock is equal to 1, or here clock event, or if that rising edge is present, that is nothing but the 0 as an input, and the clock is also 1, at that time there is a Q assigned value of the D, or Q assigned value of the D when here the clock value is equal to 1. When that clock value is 1, that means here from 0 to 1 transition is present in the system, or in the available in that system. At that time that Q value is assigned the value of the D. And here end if statement. When others means here when the difference one, or here the clock is 0, the reset is also 0, then at that time the output is null, or there is no any output. And here end case statement. And so here we are in that architecture, the firstly we are defining the begin, or begin process. So here end process is there, then here case statement, or here we are starting that case statement code, then here the end of the case, and here architecture we are starting of that D flip-flop 3, here the end for the D flip-flop 3. So in that way we are designing the VSDL codes for this D flip-flop. That is the simple codes. So here in that one we are defining the library, then entity and its architecture. That three parts we are the defining. So this one is nothing but the end of our unit 1, or here module 1. So in that we will conclude that the design entry is more efficient at the behavioral level than at the register transfer level, or here register transfer means here RTL level. Instead of that RTL level, the design entity is more efficient, or design of that HDL code is more efficient when the behavioral level, or in that behavioral level, the modules are defined in the terms of the gates. Or here AND gates or gates are present in the below that, or here the register level. So here AND gate or gate are made up of the registers. So here that is the RTL level. So here the number of reasons. The behavioral model flows from the original algorithm specifications. Thus, the model generation is a less complex and faster process than this RTL model. So in addition, changes in the algorithm are also easier to incorporate in the behavioral model, or what we are defining in that gate formation. These are nothing but the behavioral model of the system. So defining that behavioral model are very simple for. So these are the references. So here we are collected the many information from the many books. So generally I have given that the book is nothing but the book is digital system design using VHDL from the Charles Roth. From that Charles Roth we have covered these points. After the ending of this module, I will give you one assignment, and that assignment we have to complete within the 10 days and submit this assignment. So the next topic or next module we will start in this lecture, and the module name, the second module which we have to start is nothing but the module is module is the VHDL modules for the combinational and sequential logic design. Or in that VHDL modules or second module, we are writing the VHDL codes for the sequential and combinational logic circuits. So in that module or here second unit, we are having a hop adder and full adder. So in that hop adder, what is the basics of this hop adder? So in this module, am I audible? Am I audible?
Hello, sir.
Am I audible?
Yes.
Okay. The
Sir,
second is,
assignment question कुठे आहेत?
I will give after the ending of this lecture.
Okay.
So in that we have the first point is nothing but the hop adder and the full adder. So here in that hop adder or hop adder is a, or here in that adder we are adding the bits, or generally the hop adder. So the full adder, it adds 1 bit, or here A, B and C. Of that 3 bits we are adding with each other. At the time we are calling this one as a full adder. Where 2 bits can be added at the time we are calling this one as the. So these are the semantic diagrams of the hop adder and the full adder. Or in that hop adder we are adding the two, or here A is 1, B is 1 at a time, the sum is 0, A plus, or here 1, 1, 0, but here carry is generated, or if A is 1, B is 0 at a time, the sum is 1 and carry is 0. So these are the semantics of this hub adder, and from this semantics we have to define. So here the introduction of this hub adder and the full adder. An adder is a digital logic circuit in electronics that implements addition of numbers. In many computers and other types of the processors, adders are used to calculate addresses. Similar operations and table indices in the ALU also in other parts of the process. This can be built for many numerical representations like XS3 or the binary 3 coded or binary coded decimal. So here adder is a basic function of this any kind of the digital ICs. So here arithmetic logic unit. So the adders are classified into the two types. Basically the two types of these adders are hub adder and the full adder. The hub adder circuit has a two inputs. So here it adds two inputs to add input digits and generate a carry and sum. The full adder circuit has a three inputs A, comma B and C, and it adds these three input numbers and generate carry and sum. So here the diagrams of this hub adder and full adder are given to you. So here this red gate is nothing but the XOR gate. Then here the orange gate is nothing but the AND gate. The output of that XOR gate is sum. The output of that AND gate is carry. So in the similar way, here we are can we form the full adder, or in that full adder we are using the three inputs A, B and C in. Or here we are calling the third input as a carry in. Then here the output is nothing but the sum, and here C out or carry out. So the red gate is XOR gate and AND gate and the OR gate, or XOR gate when the both the inputs are same at the time the output is 0. So here in that AND gate when the both the inputs are 1 1 at a time output is 1. That is the output of this AND gate. And OR gate, the output is nothing but when any input to that OR gate is having a value of 1 at a time, the output is nothing but the 1. Or here if the input are 0 1, the OR gate output is 1. So 1 0 output is also 1, 1 1 output is also 1. So what is the hub adder circuit and the full adder circuit? Or a hub adder adds two binary digits called the addend, or here addend. Hub adder produces two outputs that are nothing but the sum and carry. The XOR is applied to both inputs to produce the sum. OR gate is applied to both inputs to produce the carry. Or here from this XOR gate we produce sum, from OR gate we produce the carry. So what is the full adder? The full adder is a 3-bit numbers. It adds 3-bit numbers where two can be referred as operands A, B, and one can be referred as a bit carried in. So it produces 2-bit output. This can be referred as output, carry, and the sum. So hub adder. So let's see how that hub adder table, or using the hub adder you can design simple addition with help of the logic gates. Or in that addition, uh, 0 plus 0, the addition is 0. 0 plus 1, addition is 1. 1 plus 0, addition is 1. But here the 1 plus 1, the addition is 0, but there is a generation of the carry that is represented as a 1. So here 1 plus 1, 1, 0. So in that the output of 1 of 1 0 is the carry out. The sum is nominal output and carry is the carry out. So hub adder, that is the A input, B input, hub adder. Output is sum and carry. That is in the block diagram form. Or in the previous one, we have seen that form is nothing but the gate level structure. Or in that behavioral logic, the gate level structure is available. So here the truth table of this pattern A is 0, 0, sum is 0, carry is 0. Or here the 1, 0, if that A is 1, B is 0, the sum is 0, but carry is also, the sum is 1 and carry is 0. 1, 1, the sum is 0, but carry is 1. A one-bit adder can be easily implemented with the help of XOR gate for the sum and AND gate for the carry. That is this truth table, or that truth table in that sum. The truth table is 0, 1, 1, 0, or that is the truth table of the XOR gate. Or in that XOR gate, if that both the inputs are same at the time, output is 0. Here 1, 1 is same, and that output is 0. And here that carry to table is for the AND gate, because here when the both the inputs are having value 1 1, the output is 1, otherwise its output is 0. So by using the basically the two gates, we can implement the XOR gate. So when we need to add two 8-bit bytes together, it can be done with the help of a full adder logic. Or other than the 2 bits, we have to use the full adder logic, because other than 2 bits, or here the 3 bits we have to add. So by 3 bits are nothing but a 111, or if in that binary form, if there's value is 111, its value is 0 in the decimal form. In that binary form, 111 is nothing but the binary value, and in the decimal we are calling this one as a 7. So hub adder image of this hub adder logic circuit, we are using the XOR gate. So how can we simply define that output? The simplest expression uses exclusive OR function, that is the sum A into B. Or here an equivalent expression in the form of the basic AND OR not is sum is equal to A or